Welcome to week 4 of the Part 107 Prep series. We've covered the core rules, airspace, and sectional charts. Now it's time for weather. This week we're going through everything the FAA loves to test about: wind, visibility, clouds, density, altitude, and how to decode METARs and TAFs. Weather questions trip up a lot of students simply because the numbers feel arbitrary. By the end of this lesson, they won't. Let's start with why this topic gets so much attention. Weather is one of the biggest reasons drone missions actually fail in the real world, especially for new pilots who underestimate it. And the FAA knows this, which is exactly why the exam tests whether you can recognize unsafe conditions and make a smart go or no go decision. Here's what we're covering in this lesson: the 4 weather categories tested on the exam, how to walk through a go/no go decision, how to decode METRAs and TAFs, and the key number and rules you need to have memorized cold before test day. Let's break down weather into the 4 categories the exam actually tests. Wind and gusts. This affects your drone stability, its battery life, and your landing control. Visibility. Your ability to detect hazards and avoid obstacles in real time. Clouds. The cloud clearance rules and your awareness of the ceiling above you. And performance, specifically density, altitude, and how it affects what your drone is actually capable of doing in the air. Keep these 4 buckets in mind as we go deeper into each one. Let's start with wind because it's the number one weather problem drone pilots face. Wind affects 4 things directly: stability. Your drone is constantly fighting to stay level. Battery life. More power is required just to hold position, which drains your battery faster than you expect. Ground track. You can drift off your intended course without realizing it. And landing control. It becomes much harder to land precisely when gusts are pushing the aircraft around. Here's the rule to remember: if wind or gusts are approaching your drone's limits, the safe answer is usually don't fly. And remember from week 1, the remote pilot in command is the one responsible for that decision. If you're not sure you can safely control the drone, you do not launch. Full stop. Now let's talk visibility and cloud clearance. 2 concepts that go hand in hand. Why does visibility matter so much? Because you need to maintain visual awareness, see hazards as they appear, and have enough time to actually avoid people, aircrafts, and obstacles. Low visibility is almost always a red flag in exam questions. If you see it mentioned, pay close attention. Now here's a number you absolutely need to memorize: the cloud clearance rule. 500 feet below clouds, 2,000 feet of horizontal clearance, and 3 statute miles of visibility. This is a favorite exam topic, so don't guess on it. Know these numbers by heart. And here's why it matters beyond the test. Flying too close to clouds risks losing your visual reference entirely and entering what's called instrument meteorological conditions, or IMC, a serious safety hazard for a drone pilot who has no instruments to fly by. Let's talk about a concept that confuses a lot of beginners: density altitude. This describes how the air actually feels to your aircraft, not what the altimeter says. When density altitude is high, think hot days, high elevations, or humid conditions. The air is thinner than it appears, and your drone has less to work with. Let's break down the 3 contributors. Heat. High temperatures reduce air density, which cuts both lift and propeller efficiency. Elevation. Higher elevations mean less air pressure to begin with, which reduces performance right out of the gate. And humidity. Moisture in the air actually displaces oxygen, further reducing motor output. Put these 3 together: hot, high, and humid, and you got a drone that performs noticeably weaker than it would on a cool day at sea level with dry air. Let's put everything together in a 5-question pre flight weather check you can run before every flight. 1. Can I maintain full control in the current wind and gusts? 2. Can I see clearly enough to detect all the hazards around me? 3. Are the clouds low enough that they're reducing my safety margins? 4. Will heat or high altitude reduce my drone's performance today? And 5, do I have a safe landing plane if conditions change while I'm in the air? Here's the rule that ties it all together. If you answer no to any of one of these 5 questions, delay the flight or change the plan. This isn't about being cautious for its own sake. It's the same professional judgment standard the FAA expects every RPIC. Let's pause here and test what you learned before we move into Lesson 8. Question 1. Why does wind reduce battery life on a drone? Question 2. What does high density altitude do to drone performance? And question 3. What are the cloud clearance numbers you need to memorize for the exam? Take a moment, work through these in your head. You should be able to answer all 3 confidently after what we just covered. Welcome to Lesson 8, where we tackle 2 terms that intimidate a lot of students: METAR, or METAR, and TAF, or TAF. A METAR is a current report, an aviation weather observation that tells you exactly what's happening right now at a given station. A TAF is a forecast, a terminal aerodrome forecast that tells you what's expected over the coming hours. Here's the good news: they use the same decoding logic, just over a different time window. Once you understand the pattern behind these reports, METARs and TAFs become genuinely predictable, and exam questions about them get a lot easier. Let's break down the pattern now. Here's the single most useful thing you can learn about METARs. They always follow the same order: station, then date and time, then wind, then visibility, then weather. If you can read each field in that sequence, you can decode any METAR the exam throws at you, even one you've never seen before. So here's my advice: don't just memorize a handful of example codes, master the pattern itself. Once the order is automatic, you're not decoding from scratch every time, you're just filling in known slots. Let's decode 3 of the most commonly tested fields using real world examples. First, wind. 180-12 G20 means wind from 180 degrees at 12 knots, gusting to 20 knots. And if you ever see VRB instead of a direction, that means variable winds. Next, visibility. 10 SM simply means 10 statute miles. If you see something like 1/2 SM, that's half a mile. And remember, lower visibility means higher risk, and it often signals a no-go situation. And finally, clouds. BKN 020 means broken clouds at 2,000 feet AGL. The cloud codes you need to know are FEW, SCT for scattered, BKN for broken, and OVC for overcast. One key rule: your ceiling is defined by the lowest broken or overcast layer, not a scattered layer, since scattered clouds don't count as a ceiling. Let's cover 2 more pieces: temperature and dew point, in TAF specific terminology. Temperature and low dew point are reported together like 18/16, meaning temperature 18 degrees Celsius, dew point 16 degrees Celsius. Here's the tested concept: when those 2 numbers are close together, fog or low clouds become likely. Close temp and dew point means rising fog risk. Remember that pairing. Now, for TAFs or TAFs specifically, there are a few change terms you need to recognize. FM means from, a change starting at a specific time. Tempo means temporary changes are expected for part of the period. And probe indicates the probability of a condition occurring without certainty that it will. The good news is TAFs decode using the exact same building blocks as METARs: wind, visibility, clouds, just spread across a forecast window with these added change indicators. Let's practice with the real example, field by field. The first example means station KBC on the 4th of the month at 18:55 Zulu time. The next example means wind from 200 degrees at 10 knots. The third example means 10 miles of visibility with scattered clouds at 3,000 feet AGL. The fourth example means a temperature of 22 degrees Celsius, a dew point of 14 degrees, and an altimeter setting of 29.92. Now let's look at the second example. This one should raise some red flags. Here we've got wind gusting to 20 knots, only 3 miles of visibility, light rain, a ceiling of 1,500 feet, and a temperature and dew point that are nearly equal, which means real fog risk. Put all that together, and this is a METAR where you want to seriously reconsider the flight. Let's test your decoding skills with 4 quick questions. 1. What does BKN 020 mean? 2. What does 18012G20 mean? 3. With the temperature and dew point reading of 18/70, what risk increases? And 4. In a TAF, what does tempo indicate? Take a minute to work through each of these using the patterns we just covered. If you can answer all 4 without looking back at the slides, you've got a solid handle on METAR and TAF decoding. Now it's time to wrap up week 4. In lesson 7, we covered wind, visibility, clouds, density altitude, and the 5-question go no go check you should run before every flight. In lesson 8, we covered METAR and TAF decoding, the pattern, the codes, practice examples, and how to spot fog risks. Coming up next, weather connects directly into performance and safety planning, building toward full practice tests as we move forward into this series. If you like a printable METAR code reference, please screenshot the previous slides. See you in the next one.